transparency.
Great, thanks. So the obligatory happy birthday slide. About 20 years ago, I joined CMU as Avram's student. I quickly developed the impression that Avram knows and is curious about basically everything, or at least everything adjacent to theoretical computer science. And I'm actually still pretty convinced that Avram knows everything. And as we all know, he's just such a positive and encouraging and brilliant person. He gets this youthful joy from the fun of thinking about problems. And I sort of suspect that somehow this is the family fountain of youth. So I wish you many, many more years of joy and good health. So the topic for today is we've been hearing all week in various ways about these new black boxes. They're transforming research, they're transforming all aspects of our lives, they're these modern machine learning models. And I'm calling them black boxes here because although we're building them, we don't really have deep theoretical principles for how and when they work or how they behave. And that's part of how we get into situations and talks that we've seen this week where we talk about things like sloppy verification, concerns of hallucination, and so on and so forth. So for ML theory, this black box situation feels a little bit like new territory after the comfort and clarity of living in sort of pack model in a world where we know about things like VC dimension. And we've been hearing about, over the course of this week, various approaches that try to build a new theory for these black boxes. In this talk, I want to take a somewhat different approach, which is to claim that black boxes are nothing new for a theory of computer science. TCS already has a really large and diverse vocabulary of tools that let us learn about black boxes without literally peeking inside, and that allow us to really build useful, reliable, trustworthy systems that use these black boxes as components. Now, of course, this claim is nothing really revolutionary or new to anybody in this room, but maybe using this framing to sort of look back and reflect on some of the tools that we have in TCS can allow us to see some new opportunities to apply the familiar tools and techniques in new ways in this new world of ML black boxes. So the claim here is that TCS is really, in some sense, a science of reliable interaction under limited observability. We already have lots and lots of core areas of TCS that ask questions like, what can we infer from limited access? What guarantees are possible without full inspection? How do we reason about hidden state? These kinds of questions, which are actually very familiar from lots of different perspectives, are suddenly central ML questions. So we want to ask ourselves what kinds of reliable interaction are possible with systems whose internal behavior can't be fully observed, and what are the relevant tools here to work on these problems? And I think two recurring TCS kind of strategies that come out for me are the design of incentives and interfaces, and the various tools that allow us to infer properties of objects in some statistical fashion. So today what I want to do is I want to take two concrete examples of TCS-style approaches to working with black boxes. How did I pick these two particular examples? Well, over the course of my PhD, Avram managed to bring me into two different nascent fields of TCS that ended up both of them exploding with interesting problems, namely algorithmic economics and differential privacy. Really, Avram had an eye for where something exciting and new was going on with the potential to be interesting and fun and elegant. So I'm going to take my two examples from those two fields from recent work of my own, but looking back to those early days when I was first learning about them. OK, so let's start with delegation. So what's the problem here? Well, the idea that we might want or need to delegate important tasks, whether those tasks are scientific discovery, or negotiating contracts and making purchases, or maybe operating our nuclear power facilities, to AI black boxes that we don't fully control or understand, sounds a little bit sci-fi. But on the other hand, humans have been delegating tasks to humans for ages, despite not being able to fully control or perceive the inner workings of those humans. We delegate to humans despite them sometimes having different incentives than us, despite them having different priorities or different information or different computational powers. And also, it's not just humans to humans. We also have institutions that delegate tasks to other complex institutions where surely you can't look inside and fully understand or control their workings. And generally, there's a science of this thing that we call delegation that's been developed in economics and is known as principal agent problems. And the key idea here is that we can sometimes design the incentives of an agent. It's not really clear to me from the language which one should be the principal and which one should be the agent. So if there's anything unclear as we go along, tell me. But the agent is the one who's going to work on our behalf. And we want to design their incentives to make them work in a way that's somehow more aligned with our interests, where we're the principal. It's the same sort of reasoning that you might see in industries where worker pay might include some sort of bonus or incentive that's tied to their performance or the performance of the company. You want to somehow align their interests. So even though you can't directly control or see in sort of to how much effort they're putting in or how hard it is for them or whether they're really focused when they're at work, you can somehow align their incentives with the incentives of the principal. And the classic challenges here that the setting tends to think about are things like hidden information. We don't really know what information the agent has access to. Hidden actions, we don't really know how much effort the agent's exerting. And things like misaligned incentives. Does the agent actually want the same things that we want? Not necessarily. So I'm going to talk briefly about a delegation project that was led by Serena Wang. Serena is now finishing up a postdoc at Harvard and moving to a faculty position at UBC. When we were working together, she was actually a grad student at Berkeley when we first started. And this is joint work also with Mike Dordan and Preston McAfee. And the contribution of this work is really to provide a theoretical model of incentives for an agent to share unknown unknowns with an evaluator. The slides also are a credit to Serena. OK, so basically we're going to focus here on a problem that's faced by regulators, which I'm going to call really sort of the fundamental problem of evaluation. If I'm a regulator that's doing evaluations, or if I'm some sort of individual that needs to outsource some task to some AI agent, how should we judge the behavior of this entity that we're regulating or this AI agent that's supposed to be working on our behalf? What metrics should we collect? What are the important things to measure in order to check their performance? So the problem that I want to talk about is not data quality or issues with our computational capacity, but rather the sort of tricky problem that regulators fundamentally don't know how to measure some notion of risk or capability. So sort of collecting or processing data, these are maybe the known unknowns, but the metrics to collect are potentially the unknown unknowns. So regulators can go around mandating collection of metrics for AI systems, but they often don't really know how to quantify things like safety. It's not clear that anybody knows how to quantify things like safety, but maybe somebody has a better idea than the regulator, and maybe that someone is the one who's being regulated. So just because a metric is unknown to an evaluator doesn't mean that the information or better information doesn't exist somewhere in the system. So a potential solution here is to try to locate that information in the hands of the evaluated agent and to think about when would that agent be willing to prefer to share metrics that are unknown to the evaluator. OK, so let's make this concrete. Imagine that you're working for some food delivery service. You're a courier. And this is run by some app. The app offers a price for each delivery based on various features of the delivery. I'm going to ask you about a few possible features. Which ones do you want the app to take into account when they're figuring out how much to price the delivery, how much to pay you for doing this particular delivery? OK, so option one is whether the restaurant tends to have a really long wait time, whether you're going to have to stand there wasting your time in order to do this delivery. I'll give you three options, then you can think about which ones you want it to account for, which ones you don't. Second option, whether it's raining outside. So the traffic's worse, it's more unpleasant to do the work, all of these things. Option three, whether the recipient is a celebrity and they give awesome cash tips. OK. Who wants the app to take into account A? OK. Who wants the app to take into account B? Who wants the app to take into account C? Fewer people. So yeah, there's a question? Celebrity. Oh, OK, yeah. So I'll just say good tippers. Yeah, you know from experience, celebrities don't tip well. So you guys tended to vote in this way. There are a lot of things I haven't defined formally about the problem. So if you were not quite sure how to respond, that's fair. But your answers align with sort of a very informal preview of the results that we're able to give in this setting, which say that under some assumptions, an agent's going to prefer to reveal metrics that differentiate the highest cost settings for them, so that the things where they really have to expend some effort from the rest, and they're going to want to conceal metrics that differentiate the lowest cost settings from the rest. So in some sense, this is not super surprising, and the hard work and the trick here is in some sense to figure out how do you formalize a setting like this, because just the idea of trying to talk formally about unknown unknowns ends up being a bit of a puzzle to try to develop the language to think about this, and a sort of formal, rigorous setting where we can make and prove some of these sorts of claims. Okay, so how do we go about doing this? A little bit more detail, given the talk, just a little bit more detail. So we model this as a principal agent game based off the very standard settings. So we're going to assume that there's some shared prior for the cost of doing a particular delivery. That's shared between the principal and the agent, where the principal is sort of the rideshare app, and the agent is you who's going to do this delivery. The principal for any particular job is going to propose some payment for doing the job, and the agent is going to take the job if the effort, the cost to them to complete the job is less than the proposed payment. The principal gets some value B if the job actually gets completed, and so the utility from the perspective of the principal is the probability that the agent actually completes the task times the difference between the value they get if it's completed and the payoff and the sort of payment that they have to make in order to get the task done. From the perspective of the agent, well, they care about they only have to do the work and they only get paid if they do the task. And then they care about this difference between the payoff and the cost, the payment and the cost to them. So that's all kind of a standard setting so far. The thing we want to add here is that maybe the agent has access to some additional variable, which is going to be cost correlated. And this is a variable that the principal doesn't even know about the existence of the variable, let alone the realization of this variable. And the agent has got to decide whether or not they would like to share this information with the principal. Now, intuitively, what's going to go on here? So if the agent shares this cost-correlated variable with the principal, now the principal can make the payments depend on this variable. So the payment for completing the ride can depend on whether or not it's raining. And then the effort is now going to be, well, is it worth it to me given this variable-dependent offered payoff? And the question is, when does the agent prefer to reveal this information? And sort of the internal reasoning of the agent goes something like this. If I'm going to reveal the variable, well, then the principal is going to be able to do better sort of pricing in the sense of they're going to be able to distinguish between the situations that are higher cost for me to complete and that are lower cost for me to complete. And so maybe there's going to be sort of more differentiation in the payments, and that's going to let me carry out some of these high-cost jobs that I wouldn't have done before. It's going to be worth my while to actually do them now because the payment's going to be correspondingly higher. On the other hand, if I conceal the X, well then from the perspective of the principal, these high-cost and low-cost jobs get bundled together. And so I can get away with doing a lot of low-cost jobs, but getting paid the overall price. Yeah?
The regular trick is to get it incentive compatible. Whatever the driver gets does not depend on its reporting. This is the basic mechanism design trick.
But we're not doing mechanism design here.
So the principal is doing it.
The principal doesn't even know the existence of the X. So we're not in a mechanism design setting. The principal can't elicit this thing. They don't even know it exists. We're in a situation where this agent...
Isn't the driver reporting X to the principal?
The driver is going to decide whether to report X, but then the existence of X is kind of outside of the sort of information space of the principal. So there's no sort of mechanism design setting here. There's just an agent who faces a choice of whether or not to be sharing X or not sharing X.
So like the difference is, if the mechanism designer knew about X, then if the agent didn't share it, they would condition on the traffic being such that they didn't share it, but here they can't do that condition.
Exactly. So it sort of shifts the problem in some slightly weird way. But it's It's true we're tempted to think of this as a mechanism design problem, but it's not really a traditional mechanism design setting. Yeah?
So C I should think of as a function of X as well.
So X is going to be correlated with C. Yeah.
Perfect.
Yeah.
And so then can the principal solve some sort of a latent variable problem and infer the existence of X from the accept-reject decisions of the agent?
So we're trying to put the sort of, there's a whole world of X's that the principal is unaware of. And so that's kind of outside of the model for us. You could try to bring them in, but in some sense that's exactly what we're trying to step away from. We're trying to get out of the world where the principal has some prior and is modeling that, and we're trying to get into just in this space where the agent has access to lots of things, lots of different signals. The principal doesn't have any prior over these or beliefs about these things. They're just kind of outside of their worldview. And then the principal's got to, and the agent's got to decide whether to come to the principal with one of these signals or one or more of these signals and offer them. And so, like I said before, one can try to show that basically there are these metrics that strongly differentiate the highest cost settings from the rest. The agent's going to naturally prefer to show these and conceal those that strongly differentiate the low cost settings from the rest. Given time, let's not do details, although there were 3 bears involved. But I think it aligns well with the intuition that you guys already had. The thing that I want to add here before we move on to our totally other setting is this question of, okay, once we've seen that there's some settings where the agent wants to reveal their signal, some agents where some settings where the agent prefers to hide their signal, we can ask, well, what if the agent could garble their signal? Commit to a particular garbling, and then share some sort of noisy version about their signal. Is that something they would ever want to do? Is it beneficial to them? Is it beneficial to the principal? So we use a very simple model of garbling. So we have a setting where they either give their signal X, which is just going to be some binary signal. They give the correct with some probability. They give the flip of the signal with the rest of the probability. And what this garbling does is that it's going to interpolate for us between the full revelation and the full concealment setting. And make a long story short, it turns out there are settings where the garbling can benefit the agent, and there are settings where the garbling can actually benefit both the agent and the principal. So the existence of the ability to send a garbled signal can actually get us into a situation where something is revealed, partially revealed, where otherwise would have been fully concealed. And maybe less surprisingly, there are settings where rather than fully revealing, as they would have done if they didn't have access to the garbling, the agent is going to, instead of fully revealing, now partially reveal. And so you can have interesting sort of interplay here. But one of the things that I like about this is that this gives an incentive to garble, even if the agent doesn't fundamentally care about privacy. It looks like privacy, but it's not for privacy reasons. They just have an incentive to give partial information here. And this is sort of a nice finding that there are settings where garbling can give you the strict Pareto improvement for the principal and the agent. So they both benefit from the existence of the option for privacy. Lots of interesting open questions here. Basically, this is one sort of first step to try to think about these unknown unknowns. But I think bringing in ideas of multiple agents, we did a little bit of work on payments, but I think there's more to be done there. I think there's a lot that one can play with these kinds of models. Question?
Could you also model this by allowing the agent to design an arbitrary signaling scheme, commit to an arbitrary signaling scheme about their true underlying cost? Is this what, so is garbling allowing the agent to do basically that?
So the garbling is less general than that. But it matches in the settings, the specific settings that we end up studying here. But I think you're going for a slightly more general setting with that language. If I'm not wrong. Okay, total change of story. Let's talk about auditing. So again, it also seems kind of far-fetched that we would be using black box, untrusted components in sensitive systems where getting things wrong could be catastrophic, and where there's no theory to support a claim of good behavior, and there's a real risk that, that any theory we might do, where there probably is no theory, but if we did some, it might be wrong, or it might be implemented wrong, or there might be high, incentive to obfuscate or to lie or whatever. So, but at the same time, we kind of do this all the time. It's exactly the setting we face whenever we want to deploy, for example, an algorithm that's supposedly differentially private. In the world of differential privacy, there aren't that many formally checked proofs of algorithms being truly differentially private. There's potential there for that to catch up, but in the meantime, we're kind of in this awkward situation where empirically, hand-done DP proofs of subtle claims sometimes have subtle mistakes. And those who claim that they have some differentially private black box might have a huge incentive to lie, or they could just have implementation bugs. So if somebody shows up with an algorithm and says, hey, this is differentially private, there's a real question. What are you supposed to do? And a response of the field has been the development of techniques of privacy auditing. And the goal here is to get high probability bounds on the privacy guarantees of black boxes, or boxes that provide sort of limited ability to peek inside. And the classic challenges here are inability to formally verify the guarantees, our limited access, or limited ability to probe the boxes, the computational costs of if we wanted to sort of retraining these algorithms on alternative data, these models, for example, and the potential sort of big incentive and big risk for these boxes to actually misbehave. So here I want to talk briefly about an auditing project that was led by my master's student, Amit Kainan. This is joined with Moshe Schenfeld. And the contribution here is a theory of how well differential privacy can be audited in only one training run. Okay, very briefly, privacy. What's the story here? In today's world, lots of computations are being done on sensitive data, whether that's training LLMs or doing statistics on medical data, take your pick. And the results of these computations, or the trained models, or whatever it is that comes out, can and do leak things about their training data. Whoops. And so this is true even if the training data was anonymized and the computations look really benign in aggregate. We've often got a problem on our hands. The sort of very aggressive threat model that we like to use is to imagine an attacker who wants to reveal whether one particular person is orange or they're blue, and they know all the stuff. So they're going to see the true data of all the other people in the data set, and they're also going to get whatever this supposedly differentially private output is, or this, computation or this model that's trained on the data. They're going to get the results of that. And the question we want to ask ourselves is, what is the knowledge gain of the attacker given that they get access to this trained model or this output of this computation? And we want to think about, they're comparing what they see in the world where the person was blue versus in the world where the person was orange. And this difference in what they see is known as the privacy loss, and this is the thing that's controlled by differential privacy. So if you know and like differential privacy, great. If it's unfamiliar, it's just a way to control that privacy loss. Okay, but it has a parameter, sometimes more than one parameter. Let's call it one parameter. It has a parameter. In order to make an algorithm differentially private, we have to add some perturbation to the computation, generally. And that perturbation hides the effect of the presence or absence of any one individual. And hopefully, despite doing this perturbation, we still get the sort of correct aggregate signal out of our process. When we develop a differentially private algorithm, we have to prove that the privacy loss is bounded by some epsilon. And the lower the epsilon is, the more privacy-preserving the algorithm is. However, privacy auditing is about empirically giving a lower bound on this differential privacy level. So to audit an algorithm, we make some sort of experiment, and then we get a statistically significant sort of piece of evidence that the DP level is not better than some epsilon prime. Why is this useful? Sort of two possible reasons. One is, if we get a lower bound from the auditing that's higher than the upper bound, whoops, something's wrong. What's wrong? Well, maybe there was a mistake in our proof, maybe there was a bug in our implementation, but something's wrong here, we should figure out what the problem is. If the lower bound is significantly lower than the upper bound, we have a gap. It's not a problem exactly, but it's an opportunity. Maybe the auditing wasn't effective enough and we should look at doing better auditing, or maybe we can do better because our theoretical analysis was not tight and we can improve it. So auditing is potentially useful for both of these reasons. And in response, there's been a bunch of work on how do you audit these algorithms. The sort of classical auditing approach is basically you want to run the algorithm over and over and over again think about it as sort of the data set where the person's blue versus the data set where the person's orange, and that's going to give you some empirical distribution of the outputs when the person was blue versus when the person was orange. And the difference in those empirical distributions is going to tell you something about the privacy guarantee. If they're very, very similar, it's very private, but if you can see a significant difference in those distributions, that's a privacy violation. This approach of classical auditing, maybe I didn't emphasize it enough, requires many, many, many runs of the audited algorithm to get useful bounds because you need to build these empirical distributions. That's computationally inefficient, and it's practically infeasible in situations where rerunning the algorithm is retraining a massive model on fresh data. So we want to think about doing something else. In response to this concern, Steinke, Nazar, and Jagielski in 2023 wrote an analysis of this idea of one-run auditing. This is dramatically better. This is an approach that requires only one run of the algorithm. And here the computational overhead is reasonable or even negligible if you manage to sort of interleave the auditing with a run you even wanted to do anyway of your algorithm. What's the cool idea here? The cool idea is that one-run auditing, instead of doing multiple runs that change one element of the data set, you do one run that samples multiple elements of the data set. So how do we think about this? We can think about it as now we have a data set where many of the entries are actually chosen at random, whether they're going to be blue or orange, or they're going to be this entry or that entry. And now our auditing process is checking how well somebody who views the outcome of the algorithm can guess which of the entries were blue and which of them were orange. If you guess very, very well, that's evidence of poor privacy. And if you guess very poorly, then it's not evidence. But it doesn't say the privacy is good. They're able to show that this one-run auditing provides valid lower bounds. It actually does tell you something about how bad the privacy is. Empirically, they see impressive results when they audit sort of the workhorse DP machine learning algorithm, DP-SGD, and they prove sort of that it tightly audits one particular differentially private algorithm. So in this work, we take on the question, more generally, what algorithms can one-run auditing tightly audit, and how well can one-run auditing reveal the true epsilon of an algorithm when it's not tight? And what we managed to show is basically a complete characterization of the power and limitations of one-run auditing. And you can summarize that characterization through three things that one-run auditing can't do. So basically, there are three kinds of algorithms that result in three gaps in the analysis for one-run auditing. The first thing that one-run auditing can't audit is the so-called name and shame algorithm. What's the algorithm here? None of these are good algorithms. These are all bad. And what I'm saying here is that one-run auditing can't see the badness. OK, so name and shame is an algorithm that takes your whole database and randomly picks one person and reveals their sensitive data. This is not good. Why can't one-run auditing see this? Well, one-run auditing has to guess well the data of a whole lot of people. But the algorithm only showed it in the clear the data of one person. So one-run auditing does not successfully give you a strong privacy lower bound. The next algorithm that one-run auditing fails on is the all-or-nothing algorithm. This is an algorithm that most of the time gives you some generic, meaningless garbage output, but every now and then it hands out the entire data set in the clear. Also a bad idea for privacy. Why does one-run auditing fail at this? Well, it's only if it manages to hit the one run where the whole data set was revealed that it has jackpot, big success in guessing the entries. Otherwise, it's guessing at random, and it doesn't guess the entries of the underlying data set very well. And then the last category of things that one-run auditing can't do are these sort of XOR kinds of algorithms. So suppose our algorithm is to output the XOR of the rows of a binary data set. The guesser isn't going to be able to reveal any value individually without knowledge of the other values, but we still have a privacy problem here. And so this is sort of both intuitively all of the gaps of one-run auditing, and also formally you can rewrite this claim as a series of theorems that basically show that while differential privacy protects every individual in worst-case scenarios from an adversary with full knowledge, the thing that one-run auditing is actually auditing. It's measuring the protection of an average individual in an average case scenario from an adversary with uncertainty. And sort of this characterization, which can be written very formally, we have an understanding of why one-run auditing was actually performing pretty well in practice, despite the fact that there are these really, really strong negative statements you can make about its power. Along the way, we also propose a particular strengthening of the one-run auditing approach. So one-run auditing, as it was previously posed, was this idea that the sort of attacker had to separately guess blue or orange for each of the entries of the underlying data set. Now, if the attacker instead had to do a different guessing problem, where they had to guess for each one whether it's blue or orange, knowing whether everybody else was blue or orange, that would be an easier guessing problem. But that's a guessing problem that wouldn't give you valid bounds on the privacy. But it turns out you can get valid bounds on the privacy that are stronger if you allow them to guess adaptively. So when they're guessing whether it's blue or orange for the ith person, they're allowed to know blue or orange for everybody up to I. And this adaptive one-run auditing ends up giving you stronger bounds. So in summary, one-run auditing's on the one hand powerful, on the other hand limited, and we're able to give sort of a new characterization of when and how to use it and to understand the gaps that it really faces. And in broader summary, we saw two TCS approaches here to building reliable, trustworthy systems from untrusted components. One was based on crafting incentives, and the other was based on probing a black box to gain provable guarantees. And I hope that this sort of reframing of things that we all, I think, at some level know from our TCS roots might be useful in helping us bring new insights in this new Wild West of black boxes. Thanks. Avram.
So in the first half, you have one kind of scenario that seems maybe interesting is one where there are possibly maybe competing agents, like competing companies that are proposing metrics to a regulator. In that case, what I imagine a company might want to do is try to figure out along what axis is their product better than everybody else's product to have the thing, you know, if you're going to propose whether you're a university or a company or, you know, having some LLM, you know, if it's going to be regulated, it should be on whatever it is the other guys are bad at, something like that. And maybe that's a way to extract information, since everyone's going to propose things the other guys are bad at.
If they're somehow orthogonal in some way, yeah. So I think that's exactly the right next step for this line of work, is to think about, you've got, you know, potentially multiple principles, but even more richly, in some sense more interestingly, multiple agents. How do they get played against each other? You know, what assumptions do you need about sort of the relationships between them and their strengths and weaknesses and preferences and abilities in order to get better elicitation. But I think that's exactly the right direction for this line of inquiry. Thanks.
So if I reveal, again in the first half,
yeah.
if I reveal this metric, won't the principal always now want to know that? Is this an irrevocable revelation?
In our model, it's just a one-time decision. But you could try to come up with a more sort of subtle model where there's some evolution of something over time, and maybe you could try to add some time dimension to it, but we're analyzing a very, very pared down version of the model.
It goes from being unknown to being a known unknown.
Exactly, yeah. I mean, and then you could still say, well, you know, I know it, but I'm not going to tell you unless you incentivize me to tell you. Right. But it becomes, then they can build the incentives. Then it becomes the mechanism design problem that we're familiar with in some sense. Okay, yeah.
For the first half of the talk, it reminded me of the scenario when you ask an LLM a certain question, it can tell you its uncertainty or how much difficulty it had answering this question, and it's later on you can ask, but the point you ask, there's also an incentive question, given the user is asking, what should I respond? But it will be interesting, for me at least, what is the sort of setting where these, machine learning models are incentivized to, basically tell how difficult, uncertain they are in their responses? I don't know.
Yeah, I think there are multiple versions of this question that are interesting. I think there's in my interaction with a particular model, how can I somehow incentivize it to tell me something about its weaknesses, strengths, uncertainty? It says it used its best model. Did it really use its best model? But also there are questions maybe popping up one level if some organization is negotiating with somebody who's providing a service and maybe using AI. I think there are many delegation tasks that we are going to be facing in the coming years, and anything we can do to get better understanding of how to structure those negotiations so that we can get better outcomes, to understand limitations of the delegation model, especially when there are going to be significant asymmetries, I think is really important. Yeah.
Okay, thank you so much.
Thank you.